Hello, my name is Eber Barbero, and today I want to talk about statics, reactions, and internal forces. This is a lecture for MAE 343 Intermediate Mechanics, Chapter 3, and it's really a review because the students that come to this class already have statics and mechanics of material, so these things they should know. But every year I have a few students that have difficulty with this topic, so I'll rather review it. All right, so okay, so then to review this topic, I'm gonna do a few examples, and I'm gonna start with the very easy examples, and then increase the complexity until we get to the level that we need for this class. All right, so what we want to do is to calculate the reactions and the internal forces. And reaction and internal forces basically are the same. The only difference is that the reaction happens at the boundary of the structure and the internal forces are internal. But they are forces anyway, and you will see that in order to calculate, we use the same method. All right, so now we start with the 2D problems. In 2D problems, we have only x and y coordinates. And therefore, we have three equations of equilibrium, which are summation of forces in x direction equal to 0, forces in y equal to 0, and summation of moments equal to 0. That moment should be labeled mz, but in 2D it's not necessary to label because it's the only moment, and I don't want to complicate things yet. All right, so the example that we're going to use today is that of a cantilever beam. So here's the cantilever beam drawn with a thickness to give it a more realistic view. All right, although for the model we only need to model the neutral axis of the beam, and like I did up down here. All right, and the first thing we do is we label the coordinate system. So because coordinate system is essential to understand each other. I mean, for you to put a report, a homework, an exam in your work, to discuss with a client, we need a coordinate system. Otherwise, we don't know what we're talking about. If we don't have a coordinate system on paper, on the drawings, it's like if you speak in English, I only know Spanish. We don't understand each other, all right? So we gotta put coordinate system. The coordinate system that we use in this class always have x along the members, okay? The structural components that we're gonna use in this class will have x along the length of the member. And then we can have y and z for other cases, but in this case, we just have y. All right, the next thing we do is we label the points of interest. So the points of interest are O and B because those are at the boundary, and also A because later on I want to calculate internal forces at that particular point. Now the cantilever beam is loaded with a vertical load P, and is supported, clamped at this end. And you can see this symbol. What its symbol means is that the beam cannot move in the x direction, in the y direction, and it cannot rotate. Now the next thing I'm going to do immediately is to replace this symbol by forces, the forces that the support will make over the structure, on the structure. So since there is a vertical load P going down, then I'm going to put reaction R sub 0 or R sub O because it's at point O, and I'm going to put it pointing up. I put it pointing up because for this simple example, it is obvious that if I load it downward, then I have to react up. But in general, you can put whatever direction you want, and then when you calculate, you will get the sign. So if you put the direction in the, say, wrong, the arrow in the wrong direction, not wrong, but in the direction that is not ideal, it may come out negative, and you know what's going on. Okay, it is negative, so the arrow should be pointing in the other direction. All right, so there's not a problem. Next, I'm going to put a moment to represent the fact that this is clamped, and this is moment m sub 0 here, which I have drawn in this way, which you will say, well, but that is wrong because if the force multiplied by the length produce a moment in this way, you gotta react with a moment in opposite to that. And it's true. But I chose to put it that way for two reasons. One, to emphasize the fact that I can choose whatever direction I want, and the problem can be solved. It's just that M0 is going to be negative. In fact, if you look here down here, when we do it, it comes out to be negative. But the other reason why I put the moment that way is because that is the way that we will have to use to draw bending moment diagrams. So from now, although in this particular lecture it's not important what direction you choose, but it's better if we can start to get used to use the convention for beams, which I will explain fully in another video, okay, or class later, okay. So okay, so then we substitute the supports by reactions, forces, and moments. Okay, and then now we use the equation of equilibrium. So the first one, summation of forces in the x direction is not applicable because we have no forces in the x direction. Summation of forces in the y direction, yes. And so I put R0 minus P, okay, R0 minus P equal to 0, and as a result, R0 is equal to P. Now, one thing that I want to caution you is that this R0 here, it looks like it's positive, but it's not because R0 points in the direction of Y. It's just because I pick arbitrarily that I like to put that as positive. So don't get hung out with, oh, I gotta use the conventions following the axis. No, 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 no. The axes are there just so we can locate points. R0, I can say R0 positive minus P negative, but I could have said minus RP plus P because anyway it's equal to 0, so I can multiply everything by -1 and everybody's right. At the end of the day, R0 is equal to P because the way I drew the arrows this way, okay? So I'm sure this is trivial for most of the students in my class, but I have to explain it, okay? So there is no questions. Next, we have to use summation of moments equal to 0. And for this problem is so easy that we could choose to calculate moment with respect to any point. But in general, it's better to choose a point like O, where some of the unknowns are not involved. In this case, it's not a problem because R0 we already know, so we could choose any point to do summation of moments. But in general, or let's say I don't want to calculate this, I want to go directly here, well, I choose O as the point, therefore the distance between R0 and the point is 0, so R0 goes away, I don't have to use it. And so once I do that, then summation of moment equal to 0, I put M0 plus PL, again M0 positive because the arrow looks like this, so a moment like that would be positive if that's the direction of the arrow, and plus P because this moment P times L has the same direction. You see, this go like this go like this. So both are positive, equal to 0, and then of course M0 is minus PL. You see, it comes out negative. So obviously the reaction is going to be this way, okay? But I can just leave it like that. You don't have to erase your paper or your screen or anything and put the arrows and recompute. No, no, it's fine like this, okay? All right, so then we have the reactions, all right? So the next slide, we're going to calculate internal forces at point A, all right? So I label point A, which is at some distance x, all right? And what is left is L minus x, all right? And okay, now like I said before, internal forces and reaction are the same, okay? But for the internal forces, you have to draw a free body diagram. Actually, this is also a free body diagram, but it's a free body diagram of the entire structure, all right? For reaction, we don't need to say that, but it is. This is a free body diagram, all right? Because I remove this symbol and I replace it by forces, okay? But for calculating internal forces, definitely I have to do a free body diagram, and in every free body diagram, what we do is we keep part of the structure. In this case, we keep A to B, and we eliminate the rest. We eliminate O to A. What you keep and what you eliminate is a question of convenience, all right? For every problem, you decide. In this case, I choose to eliminate OA because that way I don't have to compute the reactions. You'll say, well, but you already compute the reaction. Never mind. Suppose that you asked me to calculate internal forces, and I am in exam and I'm pressed for time, and the only thing I need are internal forces. So I'm not going to fool around with reactions if I can, all right? Not always I can do that, but in this case I can. I just eliminate this part so I don't see the reactions. All I see are the internal forces, okay? Again, the internal forces I pick, and in principle you could pick whatever direction you want, all right? But it's best if I use the convention that eventually will become the convention for bending moments and shear force diagrams, which will be like this, okay? All right, so then once I have that, then I do the same as before, summation of forces in the y direction, where at xa, that means at this point, and then I have v minus p equal to 0, so v is equal to p. Okay, perfect. And so again at x equal to xa, which is there, all right, where I do summation of moment equal to 0, so I say moment m, the moment that I put, all right, plus p, okay, because same direction, times what distance, L minus xa is equal to 0. And I compute the moment there, m minus p, L minus xa. If I have done this at any x, not just xa, then the moment is minus p, L minus x. And once you have these, you can draw the bending moment diagram. That's interesting, okay? We'll do that later, all right? So next, okay, we do that now. All right, so next, here's the beam, here's this. Now we have the equation, we can draw the bending moment diagram. So if we go back, what we found is that V is equal to P along the length of the beam, and the moment is given by this linear equation, all right? So there you go, okay? V is equal to P, and the moment is given by this linear equation, minus P, L minus X, which is right here, all right? With a convention that that we will discuss in detail later, but they give me the right diagrams, okay? All right, so then now let's look at another example. And so this example, a little bit more realistic, is what I call the lamppost, all right? So I got this, this structure in shape of an L, and it's loaded at an angle, okay, by a load P, at point C, all right? And in this case, I want to find the internal force at section A, and I want to do that without calculating the reactions, all right? And so, and why I want to calculate the internal forces at some section, okay? This question always comes up, why do we have to calculate internal forces? Well, we got to calculate internal forces because we want to calculate stress to compare with strength to see if the part will fail. So if we find a section, if we see a section that is notched, like this one, you see it has these notches here, then there is a reduction of cross-sectional area, and also there is a stress concentration, which are all topics that we will cover in this class later. And so we know that the stress is going to be higher there. So I want to calculate the internal forces there, so I can calculate the stresses, and then I can check where the stresses, I guess they're going to be the largest. We will probably have to check several points. I want to check if the structure fails or not, all right? So how are we going to do that? Well, like we did before, we do a free body diagram cutting at A. So we cut at A, and we keep part of the structure. In this case, I'm going to keep the top of the structure. Why? Because I don't want to calculate the reactions, and the top of the structure will give me everything I need because it's the part that is loaded, it has the dimensions, everything. So I can cut there, and that's it. All right, so I go here, and this is my free body diagram, all right? So you see I kept the top of the structure up to here, up to point A, and I put internal forces MA and R sub Y at A without worrying about the convention, okay? And so now I put these forces, and then RXA will be in the horizontal direction as well. Then I choose a coordinate system. In this case, I choose to put the X here and the Y like that, all right? And I have the dimensions, and I have the forces, and this force is 5 with components 4 and 3, okay? So I do the same as I did before. Summation of forces in the X direction is equal to 0. That will be 4 pulling that way, minus Rxa equal to 0, okay? And now you see that I put this Rxa because I already saw this 4 pulling away, so I put it like that, so the result is positive. But you could have chosen to put this arrow in a different direction, no problem. It will come out negative, that's all. So then the summation of forces in the y direction, okay, so then I say, all right, I got this minus 3 coming down, plus Rya going up, is equal to 0, so Rya is equal to 3. So yeah, I want to emphasize this. The direction of the arrows I chose because I'm experienced, and I can look at the figure and I can guess in which direction everything is going to come out positive. So the example is nice for teaching, but it's not necessary. You can put them blindly, and then you get what you get, okay? So then we do summation of moments, and then we say, okay, MA, which now I'm saying is positive. So everything that it turns out for now, for this example, for this particular drawing, anything that is an MA like this, I say is positive. And then, of course, I have to subtract 3D because there is this 3 coming down multiplied by this distance D, which put a moment opposite to that arrow. And if I said this arrow is positive, okay, then the opposite has to be negative. And then I have a 4 pulling away this way, which is a component of this force in that direction. All right, and again is doing a moment like that, yes. And so 4e, so put my minus 4e. And then now I calculate MA 3D plus 4e, or I will come out positive again. Okay, so I got my internal forces. All right, so okay, for this lecture, we have some conclusions. The reaction and the internal forces you have seen, they're calculated the same way, but the calculation of internal forces require a free body diagram. And for now, there is no need for a sign convention. Once you draw an arrow, that is positive. If the answer comes out negative, we understand what it means. There's no problem. But later, to do diagram, we will follow a strict sign convention. There will be homework assigned on web work at this address. Okay, and the next lecture will be reaction and internal forces in mechanical components. So more of the same, but a little bit more complicated and more applicable to this class and to the follow-up class, which is machine design. For now, thank you very much.